Welcome to The Explainer. Today, we're diving into something we literally look at every single day, but probably rarely think about: the comprehensive structure of LED displays and the cutting-edge MIP technology that's totally shaking up the industry. We're going to go on a bit of a journey today, starting from the massive, awe-inspiring scale of those giant city screens, all the way down to the microscopic science of the individual pixels that actually make them glow.
But before we zoom in on the technical stuff, we really have to appreciate the macro-level impact of LED tech. When you look at a vibrant, modern cityscape, you aren't just looking at screens. You're seeing dynamic media that literally illuminates our world. These things are absolute powerhouses, integrating complex electronics, optics, and communication networks into architectural marvels. If you've ever stood in a major city center at midnight and felt like it's high noon, well, you've experienced the raw power of LED displays. But how exactly do they pull this off?
Well, here's our roadmap for this explainer. 1. An introduction to LED displays. 2. The modular building blocks. 3. Breaking down key display parameters. 4. The actual science of pixels. And 5. MIP technology versus conventional setups. All right, let's jump right into Section 1. An introduction to LED displays.
So one of the absolute most defining features of an LED display, especially when you compare it to an LCD or a projector, is its insane longevity. We are talking about a lifespan of 100,000 hours. Let's just put that into perspective for a second. If you turned on a brand new LED display today and you left it running continuously, 24 hours a day, never turning it off, it would keep going for over 11 years. That exceptional rock-solid stability is exactly why this tech absolutely dominates the outdoor space.
Which brings us to Section 2, the modular building blocks. Let's look at how these things are actually built.
The structural foundation of these massive screens is called the cabinet. Think of these cabinets as the giant industrial Lego bricks of the digital display world. They're built from precise die-cast aluminum alloy, and a typical cabinet measures 1,200 by 1,200 millimeters with a depth of about 121 millimeters. And they are heavy, weighing in at a hefty 55 kilograms each. Because they're engineered with specialized connectors and carry an IP65 rating, they effortlessly shrug off harsh outdoor environments. We're talking everything from freezing negative 20-degree winter weather to scorching 50-degree summer heat.
Okay, so if the cabinet is the heavy structural foundation, what actually lights up? Well, inside each cabinet are several smaller, completely seamless blocks known as LED modules. These modules, which often measure about 400 by 200 millimeters, are the pieces that hold the actual LED lights, and they are expertly engineered to fit perfectly side by side. That way, the viewer sees one continuous, flawless image, rather than some clunky grid of separate panels.
And that right there illustrates the absolute genius of what we call modular modifiability. Because the whole system is built on these interlocking cabinets and modules, an LED screen doesn't have a fixed, predetermined size. This structure means screens can be as tiny as a single square meter or as absolutely gigantic as thousands of square meters, wrapping all the way around a sports stadium. It's a fully custom product built from standardized, off-the-shelf blocks. Let's move on to Section 3, Key Display Parameters Explained. The most fundamental metric you're going to hear about is pixel pitch. That's simply the physical distance between adjacent pixels on the screen. But why does that matter? Well, it directly determines the resolution and the optimal viewing distance of your display. The smaller the pitch, the tighter the density, meaning you can stand right up close and still see a super clear image. For indoor products, pitches are typically 3.9 millimeters or smaller. But for those huge outdoor billboards, they use much larger pitches because the viewers are looking at them from far away.
Next up, we really need to talk about light itself. First is luminous flux. Put simply, this is the total amount of raw light emitted by a source in all directions, and we measure it in lumens. When you want to know the absolute raw light output muscle of an LED chip before that light is shaped or directed by lenses, you are looking at its luminous flux. This is also closely related to luminous intensity, measured in candelas, which takes those lumens and relates them to a very specific beam angle. Now you have to contrast that luminous flux with illuminance. Illuminance is measured in lux, and it tells us the amount of light that's actually arriving at a physical surface. If luminous flux is the water leaving a hose, illuminance is how wet the ground gets. This is a vital metric because a display's perceived brightness, its luminance, needs to literally cut through the ambient illuminance of whatever environment it's placed in.
Okay, let's actually put this knowledge to the test with a real-world scenario. Imagine you're managing a big project in Sydney, Australia.
You need to install an outdoor LED screen facing north, which, remember, in the southern hemisphere means it is pointing directly into the intense daytime sun. If you have 4 different display options with brightness levels ranging from 5,000 to 13,000 nits, which one of those is actually going to work in this harsh environment?
Well, here's the answer. An outdoor screen facing the direct sun requires a brightness greater than 8,000 candelas per square meter, or nits. So those models maxing out at 5,500 or 5,000 nits, they would completely wash out in the Australian sun. You wouldn't be able to see a thing. The only viable options are the units outputting 10,000 or 13,000 nits. If you don't understand your brightness parameters, your incredibly expensive screen is essentially useless during the day.
All right, diving even deeper now. Section 4, the science of pixels.
There is actually a massive physical difference in how individual pixels are built. Older DIP-style LEDs have those distinct, long legs, and they're usually arranged in a 1R, 1G, 1B configuration, meaning one separate red, green, and blue diode are physically bundled together to make a single pixel. But the SMD, or surface-mounted device, encapsulates all 3 of those color chips into one incredibly tiny flat package. This microscale packaging difference dictates everything from the pixel pitch to the viewing angle, which can actually reach up to 120 degrees horizontally. It even affects the color depth, pushing modern displays from 8-bit systems with 16 million colors to mind-blowing 16-bit systems capable of rendering 281 trillion colors.
But how do these tiny chips actually create light in the first place? The working principle is called electroluminescence. Inside the LED is a microscopic semiconductor PN junction. When electricity is applied, electrons and holes in this junction recombine. And as those electrons transition to a lower energy level, they release that excess energy as photons, which is light. The specific color you see is dictated by the chemical elements used inside. Gallium arsenide produces red light, gallium phosphide gives us green, and gallium nitride produces blue. It's literally chemistry creating color.
Moving on to our final stop. Section 5, MIP technology versus conventional.
The sheer magnitude of the performance leap you get with MIP technology is just staggering. We are definitely not talking about marginal incremental improvements here. When you compare MIP to conventional indoor chips, MIP drives a brightness leap of up to 560%. It jumps from around 600 nits to an astonishing 4,000 nits indoors. And for outdoor signage, the contrast ratio jumps by 180%, going from 3,500 to 1 up to a massive 10,000 to 1 ratio. It's a real game changer.
So how is MIP achieving these crazy numbers? Basically, by fundamentally upgrading the hardware. MIP technology shrinks the pixel pitch down to a microscopic P1.2. That is just 1.2 millimeters between pixels. But alongside that blinding brightness and deep contrast, MIP also introduces intense physical protection. It boasts superior anti-collision and anti-scratch properties, anti-moire visual filters, and incredibly high resistance to moisture, salt spray, and mildew. So it's not just a dramatically better picture, it's a vastly more robust product all around.
Which really leaves us with this final provocative thought. We started this explainer by looking at massive glowing city skylines, and we zoomed all the way down to a 1.2 millimeter pitch where microscopic electrons generate perfectly calibrated photons. With MIP technology shrinking pixels to near invisibility while skyrocketing contrast and physical durability, when will the line between a digital display and physical reality completely vanish? Just think about that the next time you walk past a towering digital billboard. Thanks for joining me on this explainer, and keep exploring.